is today. Vigorous and still growing. Bustling with life and enterprise. Over the vast expanse of America, men have dreamed and built prodigiously. But to give substance to the dreams, there had to be a material equal to the task. That material was and is steel. Today, out of every 2,000 pounds of all metal used in America, over 1,800 pounds are iron and steel. But why steel above all other metals? What is it? Where does it come from? How is it made? The answers are to be found in many places. But first we must consider iron, for steel is iron. So let us go back 1 billion years or so and begin that part of the fascinating story. Tumultuous geological evolution, the Earth began to cool. In the primeval basins, the oceans appeared. And for centuries, the rains continued to fall upon the smoking, blasted surface. As the waters flooded over the Earth, they loosened and dissolved the soil, and much of it was carried along by streams and rivers, eventually finding its way into the lakes and oceans. Heat and pressure eventually transformed sediments into layers of rock. Continuing upheavals in the cooling crust often caused them to be folded and cracked and thrust up to be exposed to the eroding effects of the elements. Sometimes a mass of molten material would boil up from below. Often rich in iron from the crucible of the Earth's interior, the molten material usually dissolved the host rock and replaced it, solidifying into a mixture in which the concentration of iron is quite high. This we call iron ore. There are billions of tons of iron ore deposited around the world, but of course it must be converted to other forms before we can use it. To demonstrate simply the basic steps in the next part of our story, let us call up from an earlier time an iron master, one who learned from the ground up. Obviously, the ore had to be removed from the ground. So, whether it was found right on the surface or had to be mined, the first step was... Digging! Yes, digging. The ore was often found in more or less inconvenient places. So the next thing to be done was... Hauling? That's right, hauling. The next step, a most important one, was... Smelting. That's correct. Smelting, getting the iron out of the ore. For this, a large furnace, often made of stone, was necessary. There had to be a huge bellows to blast air through and make the fire hotter. And there also had to be... Charcoal and limestone. Correct. Charcoal and limestone. The charcoal was fuel for the fire. And while our friend here didn't know it, it also furnished carbon for chemical reactions that helped free the iron in the ore. The limestone was put in because it soaked up impurities, forming a slag which could be discarded. The smelting process was begun by dumping layers of ore, limestone, and charcoal into the furnace. Into the furnace. Was ready to be tapped, and the iron which was now melted, ran out the bottom into a trench. Since this rather resembled a family of little pigs, the iron came to be called pig iron. Now the iron had to be turned into something useful, and casting the molten metal was one of the ways this was done. When it cooled, this cast iron was very hard, and many useful items could be made from it. However, it was not practical for some things because it was quite brittle. In another method of converting it into useful form, bars of the iron could be reheated and refined in forges and beaten into various objects. Called wrought iron, this kind was strong and tough and could be made into other useful items. However, for some things, it was too soft. Obviously, there was a difference in the two kinds of iron. Our friend didn't know exactly why this was, but he learned that he could make even another kind by putting the soft iron in clay pots, adding a certain amount of charcoal or other carbon, and making his fire hot enough to melt the iron. Getting enough heat was difficult, but this was the secret of the process. The iron he obtained this way was very special, for it combined the best qualities of the others. It was even given a special name: steel. It could be shaped by hand. It was supple and flexible and would not shatter. Yet it was hard and tough and would stand up under difficult conditions. But because it could be made only in small quantities, steel was rare and precious, worth its weight in gold. Even as late as the founding of the colonies in America, steel was very scarce. But iron was so essential that one of the first industries was an iron works built on the Saugus River in Massachusetts in 1644. The original house of the ironmaster still stands near the Saugus, and the iron works itself has been so faithfully restored that we can actually see how iron was made in the early days of our country. The iron ore and charcoal and limestone were dumped by hand into the top of the blast furnace. The waters of the Saugus were put to work turning giant wheels that in turn operated such things as the big bellows that forced air through the blast furnace. The furnace was built of native stone and could make about 3 tons of iron in a day. Once or twice a day, the tap hole was opened, and the molten iron flowed out to be cast in pigs or other items. There were forges where the bars of pig iron were heated and refined, and a 500-pound iron trip hammer for pounding them into high-quality wrought iron, and a rolling and slitting mill where the bars were guided through by hand to make strips and rods. This project, big for its time, was built with the savings of many individuals in much the same way that large companies are created today. During the Revolutionary War, iron played an important role. There was some steel for swords and small weapons, of course, but it was iron for cannon and cannonballs and pots and kettles upon which the Continental Army depended. There was even an iron chain with links weighing 100 pounds apiece stretched across the Hudson to keep the British from coming upstream by ship. Also, George Washington was the son of an ironmaster, and Valley Forge, which became a symbol of early American courage and determination, was itself originally an ironworks. After the war, the number and size of blast furnaces and forges grew rapidly, and the iron that flowed from them became more and more essential to the nation. Again, it was investment by individual stockholders that made this expansion possible. Now railroads appeared on the land, and steamboats on the rivers, and factories and machinery in the cities. A small amount of steel was available for special uses, such things as the blades of the history-making McCormick Reaper. But even as late as the Civil War, iron was the only metal in abundant supply. However, as the guns of war fell silent, this was about to be changed. In 1864, 2.5 tons of steel were made in minutes in a device called the Bessemer converter, and the age of steel had arrived. Now, at last, steel could be made in quantity and at low cost. To raise money for further growth, iron and steel companies issued new shares, and in the stock exchanges of the day, they were eagerly purchased by investors large and small. On every side, the spirit of freedom and individual enterprise acted as a catalyst, and the stage was set for America to take her place on the world scene. Unparalleled growth and development of America. Steel because of its strength and versatility and low cost. But ask now, what of steel making today? First of all, iron and steel are produced by 275 companies in America, and the industry they comprise has increased almost tenfold in half a century. More than 500,000 people have jobs in steel, and ownership of the companies is shared by several times that number. The men who manage these enterprises must make decisions that often involve hundreds of millions of dollars. Well, there is nothing small about making steel. Throughout the industry, marvels of engineering have become almost commonplace, and there are complex, scientifically precise methods needed to meet modern demands. But despite new technology, the basic steps are still the same. For example, we must still wrest the raw materials from the earth. Remember, our old friend had to do this too, but he had to find ore that he could dig and haul away 100 pounds or so at a time. Today, it's tons at a time. And while much of it is still used just as it comes from the mines, low-grade ores, once thought worthless, are often used. One of these, called taconite, is harder than glass. That's a machine for drilling taconite. Jets of flame pierce holes in the rock. The holes are filled with high explosive, and then giant-sized shovels scoop up the rock and it's hauled away by the trainload. The cars are dumped 2 at a time by specially designed equipment. In huge plants, the rock is pulverized and washed, and richer iron ore is separated out magnetically. Now, the iron-rich powder is fed into large drums to be made into pellets. Moving belts next take the pellets to a furnace where they are hardened by baking. Finally, the pellets are loaded on ships and transport them to the places where steel is made. The ships are of a special kind, the newest designed to carry over 20,000 tons of ore. In addition to the iron ore mined in the United States, millions of tons are brought in from Canada and other countries. Now, great quantities of coal must also be clawed out of the ground. Ton upon ton of limestone must be quarried, and alloying elements are brought in from all over the world. At the mills, the coal is baked into coke. The raw materials are dumped into huge piles, and only now are we ready for the next step. Going back to our old iron master, his next step was... Yes, smelting. However, blast furnaces have changed somewhat, as might be expected. Giants such as this, amazingly engineered, can turn out 3,000 tons of pig iron a day. The raw materials are still hauled up and dumped in the top, but now it's done by the carload. And today's iron makers have sensitive instruments to tell them what's happening inside. After the furnace is tapped, the molten iron flows as before, flaming and hissing in the runners. The scenes are weird and spectacular, blazing with heat and fiery glare. The work may look dangerous and even frightening, but because of training and proper safeguards, the records show that this is one of the safest of all industries. In fact, steel workers are safer on the job than they are at home. Now the molten iron must be taken away from the blast furnaces to await the next step, transformation into steel. In one of the ways this is done, enormous machines charge tons of scrap steel into long banks of open hearth furnaces. Now molten iron is added in exact proportions, and men watch intently as batches of steel boil at almost 3,000 degrees. It takes rugged men to make steel, but today's steelmaker must have knowledge and education too, for steel must be made with care and precision to meet today's demand for quality. In another method of making steel, furnaces that depend upon electricity are used. Enormous electrodes flashing in blinding arcs generate heat with thousands of volts of electricity. Most stainless and tool steels are made in this type of furnace. Here's still another way of making steel, called simply the basic oxygen process. And here we see one of the newest of the new looks in steel. Scrap steel is charged into the furnace with speed and efficiency, and molten iron is added quickly, for every minute counts. Here is the heart of the process, a pipe through which pure oxygen is blasted at supersonic speed. Combining with the materials in the furnace, the oxygen generates its own heat to purify the iron into steel. The furnace is equipped with modern electronic controls to make up the recipes for the hundreds of kinds of steel that we use in our homes, for transportation and construction, and in industry. New equipment such as this is costly, but it is absolutely essential to progress. When the signal is given to 4, just about a half hour has passed since the raw materials went in. And now, this is steel. In the midst of this enormousness and scientific control, some things are still best done by hand. Alloying elements are added a bag at a time, like adding sugar to a cake by the grain. But this small, last-minute addition will bring the composition of the steel to exact specifications. But molten steel, however made, is an intermediate step, and it cannot remain long in the brimming ladles. The ladles are now swung into place over long files of empty molds, and the molten metal is poured out in an operation called teaming. Later, the molds are stripped off, and at last there are ingots of steel in solid form. Now let us return for a moment to our old friend. He made steel in a different way, but the end result was still an ingot of steel. Of course, a plain lump of steel is of no use, so as may be remembered, he had to hammer it into shape. Ingots today are usually 15 or 20 tons, but they have to be shaped too. However, again, the methods are rather different. The great clumsy chunks of red-hot steel are flipped and shunted about with casual ease by men sitting in air-conditioned comfort. With fingertip control of enormous machines, they push the ingots through rollers that act like giant ringers, squeezing the steel repeatedly into longer, thinner pieces. Sometimes the steel is rolled out like cookie dough into large slabs. Each piece has its surface scoured by flame to remove small imperfections. Then it is cropped to length by huge shears. Slabs are made in many shapes and sizes, and they go through many different kinds of finishing. They are slammed through rollers that break the scale that forms the surface. Then they are trundled down long tables to finishing stands where they are rolled and re-rolled, becoming thinner and thinner. They may be taken off as plates of steel to be made into railroad cars or storage tanks or the like. Or at other times, the steel is rolled into a very long, thin sheet. Men keep watch as automatic devices control the whole operation. For as the strip becomes longer and thinner, it must go faster. It hurtles out of the last mill at 30 miles per hour and plunges into a cooling spray, and finally is rolled up automatically into a huge coil. When cold, such steel is sometimes put on other mills and rolled again, giving it a smoother and harder finish for auto bodies and appliances of many kinds. And some of the steel is given even further treatment. It is coated with molten zinc to make it into corrosion-resistant galvanized steel. Or it is cleaned in acid and plated with tin to make better, thinner, and more economical tin plate to protect our foods and beverages. Some steel is rolled into pipe that carries oil and natural gas thousands of miles across the country. For special purposes, such as the drilling of oil wells, solid bars of steel are made into seamless pipe. In other operations, steel is rolled into the structural pieces we see in bridges and buildings. Some steel is formed into bars, or it is rolled into rods and stacked in glowing coils. Later it may be drawn out into thousands of feet of wire for fences, nails, springs, and bridge cables. But making steel still demands control of tremendous force. In a specialized phase called forging, ingots of 100 tons are handled with ease. Literally squeezes the ingot into shape with as much as 15 million pounds of pressure. Smaller pieces of steel are pounded by great mechanical hammers to impart added strength to the metal. Thus, we have seen that many of the steps used by the old iron masters still have counterparts today. But there is a great and fundamental difference. Our old friend gained his knowledge by trial and error. He was remarkably successful most of the time. Today, because of costs and demands for quality, a more scientific approach must be taken. In modern steel company laboratories, research is playing an ever-increasing part. This research is conducted in many directions, both theoretical and practical. On the practical side, new ideas and equipment must be proved on a small scale before millions of dollars are invested in new processes and equipment. And there is a constant search for ways to make more steel and better steel at the lowest possible cost. Experiments conducted here have already introduced new production methods which are in limited use now and will soon be widespread. For example, here is a new process in which molten steel is forced into a mold by air pressure. It takes split-second timing to control the process exactly, but this represents a shortcut in the making of high-quality stainless and alloy steel. In another new method, ladles of molten steel are sealed in vacuum chambers and stirred magnetically. Bubbles of trapped gases that would weaken the steel are drawn off. And for very special steels, ingots hooked up to large electrical transformers are also sealed in vacuum chambers and remelted like candles. This gives even purer, super-strength steels like those used in space vehicles. In one of the most important new developments, called continuous casting, steel is poured into a bottomless mold. In descending, it cools and solidifies. The steel comes out like a ribbon of red-hot toothpaste to be sliced off in any desired length. Other experiments have not yet left the laboratory. Here, powdered iron is poured into a hopper and pressed into strips. It is then heated and rolled, producing a sort of instant steel. In another experiment, a sample of steel is suspended in a magnetic field within a vacuum chamber. It can then be melted without contamination. This is all a part of the drive for progress in steel today. But the future lies in another, more fundamental kind of research, that which probes into the nature of iron and steel. With microscopes that use streams of electrons instead of light, magnification of 200,000 times reveals the intricate structure of steel. Also, steel must be studied at 400 degrees below zero for its use in outer space. And it must be tested at 1,000 degrees above for jet engines. Even with our present knowledge of the iron atom, we have learned to use only about half of its potential strength. But with research, a whole new era is coming, one with new kinds of steel and new uses. Steel foil is now rolled in sheets thinner than tissue paper. A simple demonstration shows that steel foil is far stronger than any other kind. There is thin, perforated steel that is almost transparent, but still strong and durable. And there are new super steels so strong that a pencil-thin bar can support the weight of a railroad car. New steels are making possible revolutionary types of buildings, such as this one, in which each wall rests upon only 2 points. This is only a small part of what is to come, for America itself is entering a new era. No one can say with certainty what changes the next 100 years will bring, but the vast preparations that will enable Americans to venture into outer space are symbolic of them all. As before, steel is playing an essential role. It forms the framework of giant structures. It is in the heart of every rocket. But whatever the changes and whatever the challenges, steel remains the material equal to the task.